Welcome back to part 3 of the static timing analysis series. In the previous video, we introduced clock-to-Q delay and treated it as a single timing parameter. Today we are going to refine the model. In reality, clock-to-Q is made up of two different timing values, clock-to-Q Contamination Delay and clock-to-Q Propagation Delay. We will learn what each one means, why they both exist, and how they affect the setup and hold constraints. Let's get started. Before moving forward, let's quickly review the flip-flop timing parameters from the previous video. We learned that setup time is the minimum amount of time data must be stable before the active clock edge, and hold time is the minimum amount of time the data must remain stable after the clock edge. Clock-to-Q delay is the time between the active clock edge and when the flip-flop produces valid data at its output. For simplicity, we treated clock-to-Q as a single delay. Now let's make that model more realistic. A real flip-flop doesn't have just clock-to-Q delay. Instead, it has two. Clock-to-Q Contamination Delay. This is the earliest time output Q can begin changing after the effective clock edge. Think of it as the fastest possible response of the flip-flop. And Clock-to-Q Propagation Delay. This is the latest time the output Q is guaranteed to be stable. Think of it as the slowest possible response of the flip-flop. As you can see in the timing diagram, the output doesn't change at once. It doesn't change in one exact instant. It begins changing after the contamination delay and reaches its final stable value after the propagation delay. Now let's see how this changes the timing equations. Previously, we used a single clock-to-Q delay. Now we can be more accurate. Hold constraint. The hold constraint checks whether the data arrives too early. Since we are interested in the earliest possible arrival, we use the clock-to-Q contamination delay. So instead of using generic clock-to-Q delay, we now use clock-to-Q contamination delay together with the contamination delay of the combinational logic. Setup constraint. The setup constraint checks whether the data arrives too late. Since we are interested in the latest possible arrival, we use the clock-to-Q propagation delay. So the setup constraint now uses the propagation delay of the launch flip-flop together with the propagation delay of the combinational logic and the setup time of the capture flip-flop. Let's go back to our example and update the timing analysis. Before we move forward, if you found the content valuable, I will appreciate if you subscribe to support the channel. Now that we have updated the flip-flop timing values and reduced the clock-to-Q contamination delay and clock-to-Q propagation delay, let's check the hold constraint again. We will look at the path from Q0 to D1. The hold time requirement of the capture flip-flop is 3 nanoseconds. The launch flip-flop has a clock-to-Q contamination delay of 2 nanoseconds, and the contamination delay of the combinational logic is 3 nanoseconds. That gives us an earliest arrival time of 5 nanoseconds. Since 5 nanoseconds is greater than the required hold time of 3 nanoseconds, the hold constraint passes. Notice that the hold analysis will always use the clock-to-Q contamination delay because we are checking the earliest possible arrival of the data. Now let's check the setup constraint. We will start with the path from X to D1. Then this path starts at the input rather than a flip-flop. We only consider the propagation delay of the combinational logic and the setup time of the capture flip-flop. The combinational logic takes 5 nanoseconds and the setup time is 8 nanoseconds. So this path required a minimum clock period of 13 nanoseconds. Now let's look at the path from Q0 to D1. The launch flip-flop contributes 3 nanoseconds of a clock-to-Q propagation delay. The combinational logic contributes 5 nanoseconds of propagation delay. Finally, the capture flip-flop requires 8 nanoseconds of setup time. Adding those together, this pass requires a minimum clock period of 16 nanoseconds. Since 16 nanoseconds is the largest requirement, our clock period must be 16 nanoseconds or greater to satisfy every timing path in the design. Finally, let's choose the system clock frequency. A clock period of 16 nanoseconds corresponds to a maximum operating frequency of 62.5 MHz. That means any clock frequency at or below 62.5 MHz will satisfy the setup constraint of every timing path in this design. We have now covered the three main timing parameters of a flip-flop: setup time, hold time, clock-to-Q, including both its contamination propagation delays. At this point, you know enough to analyze a complete timing path. In the final part of this series, we will introduce one last concept that affects every synchronous design: clock skew. We will learn what positive and negative clock skew are, how they affect setup and hold timing, and how engineers minimize clock skew in real designs. I'll see you back in part 4.